Might as well do question 2 as well. A student investigates the oscillations of a uniform rod of length L, which is pivoted at the top as shown. Describe how to determine accurately the period T of the oscillations of this rod. Okay, it says the word accurately, so I know what I need to add to my answer here. So first of all, using a stopwatch and then timing over multiple full oscillations in order to get that accurate part in there. So here's an answer I would put using a stopwatch. Time, how long it takes to complete and here I want to say 10, 5, 6, 7, whatever, 10, but I need to say full oscillations here. And then, as it's a 2 marker, try to separate it into 2 sentences. Divide this time by 10 to get the time period, capital T. There we are. Job done. I have to change over to my red pen. That green one's running out. Next part, we have the relationship between frequency f of the oscillations of the rod and its length is f equals 1 over 2 pi 3g over 4l. So we've got an equation for, sort of this sort of situation where that's the length and all of the center of mass is concentrated at the end. So we've got t equals 2 pi root L over G, something we're familiar with. 1 over time period will give us the frequency. So normally we'd expect to see 1 over 2 pi root G over L. And then when we look at this one, we've got this 3 and a 2, and that must be the adjustments associated with it being a solid uniform rod rather than a bob on the end of a string. Either way, that equation should look familiar to you. The student varies the length of the rod and determines the time period capital T for each length. The student plots a graph of T squared against L shown in this graph. The line of best fit has already been drawn. So looking at this graph, I've got T squared against L, which means I'm expecting to have to take this equation and get it lined up with what this graph is. So on the y-axis I've got T squared, and on the x-axis I've got L. So here we go. So show that the gradient of the graph, this graph, is given by 8 pi squared over 3g. So let's start by copying and pasting the equation that they've given us. So 1 over 2 pi square root 3g over 2l, and I'm working from a graph that's got t squared on the y-axis and l on the x-axis. So let's start by substituting in t equals 1 over f. Let's put that in there to get 2 pi 2l over 3g. And then we'll say t squared equals, just square everything, t squared is 4, pi squared is pi squared, and then we're left with d times 2l over 3g, t squared equals, and then I've got 2 times 4 is 8, pi squared, leave a little bit of a space for my l, underneath that I put my 3g, put brackets around that, and then do my y equals mx plus c, and then I've got that lined up really well. It's a shame I wrote so big there and had to scribble through some of the things we're going to need for the next questions. Okay, the gradient of the line of best fit on figure 2.2 is 2.64. Now, it is unusual for this type of exam to not ask the students to do two. Typically, there'll be a table of results. A couple of these points will be missing, and the student would be required to fill in the rest of the table of results with some uncertainty associated with that. Plot two of the points on the graph, then draw the line of best fit, and then work out the gradient of the line. So it is very, very unusual for an exam not to ask the students to do that. So I can only assume that this might be because it's post-COVID or something, and your typical A-level student might not have had the same practical experiences as they would normally have. I don't really know. Either way, let's do this question. So use this gradient of the line, so dy by dx. They've given us the number of 2.64, and our analysis of the equation, whether we've been successful or we're just copying the information that they've given us already, that number is equal to 8 pi squared over 3g. Therefore, g would be equal to 8 times pi squared divided by 3 times the value of the gradient. It's interesting how they've managed to get 3 sig figs out of a graph that's just got big squares and little squares, but I'll let it go. So on my calculator, that is 8 times shift pi squared equals, divided by open brackets 3 times 2.64 close brackets equals 9.9693 meters seconds to the minus 2. And I guess I've got to follow their lead. That number that they've given us there is to 3 sig figs. Therefore, I'm going to write my answer to 3 sig figs. It's going to be 9.97. Okay, now we've got some graphing skills being put upon us. Draw a line of worst fit on graph 2.2. So here's graph 2.2, line of worst fit. Now, my recommendation would be use a pencil, but I'm just going to use a pen in order to make it stand out a little bit better on the video here. Get my ruler. Now, here with the lines of worst fit, we have a choice, and the decision that I make will depend on the following. What I want is my line of worst fit to create a situation where it's very easy for me to determine, quick and easy for me to determine the gradient. I already know I'm going to be doing the steepest line of worst fit rather than the shallowest. But let me line up my ruler with the shallowest just so you can see what I mean. And the reason why I'm not going to go with the shallowest is what I want to draw is a line of worst fit that crosses. So on the y-axis, this is fine, but also crosses on the x-axis. And this one kind of doesn't there. Can you see that? Just misses out. Whereas if I do the line of worst fit, that's the steepest line of worst fit. So that is uppermost error bar, lowermost error bar, and I must check that I'm going through all of the error bars in between, which I am. Now when I draw my line of worst fit, I can extrapolate it right over to the edge of the scale, and it just makes reading the dy and the dx real easy. So as I'm on my graph, I might as well write dy equals, and now it's just a case of counting up 0.1, hang on a minute, 0.1, 0.2, 0.3, 0.4, 0.42, 0.42. And here I can do my dx in the same way. Now, they're always, one of the scales is going to be quite gnarly to read, and this one is gnarly to read. So looking at this, each little square is worth 0.004 by the looks of it. So 0.04, 0.08, 0.12, 0.012, yeah. So 4 for each of those. So counting my dx, it's, let's go 2, 4, 6, 8, 10, 12, 14, and 4. So 0.144. do that on my graph so that the examiner can see where I've got my numbers from in my workings later on. So use your line of worst fit to calculate the percentage uncertainty in this value of G. So that percentage uncertainty is going to be the same as the percentage uncertainty in line of best fit versus line of worst fit. So if I work out the gradient of my line of worst fit, so dy by dx, I might put subscript worst. There, I can now put the numbers that I'm using here, 0.42 divided by 0.144. Put that in on my calculator. And so I've got there 2.92. And then my percentage uncertainty will be the difference, so 2.92 subtract 2.64 divided by the most accurate, so that's the line of best fit, 2.64 times by 100%. My workings seem to have gone off on the wonk here a little bit. So 2.92 minus 2.64 equals divided by 2.64 equals times by 100 equals, and I've got 10.6060. It's kind of tricky to know what to write here in terms of the percentage uncertainty, as they've sort of forced our hand a little bit with this 3 sig fig, so I might just write that as 10.6. Although 11 I think would also be acceptable. Okay, final part of this question is use the true value of 9.81 to evaluate the accuracy of the student's value of G from this experiment. Include a calculation in your answer. Okay, I think it's easiest to do the calculation first. So it's that value of G we need to compare to the actual value of G. So if we were to do percentage accuracy, we would do the difference, so that's going to be 9.97 subtract 9.81, all divided by the most reliable value of these two, which is 9.81 times by 100% equals, so 9.97 minus 9.81 equals divided by 9.81 equals times by 100%, and I've got 1.6% accuracy there, and we need now to compare that number 1.6% accuracy to our uncertainty of 10.6, and this percentage is well within that percentage. So that means that the student's value for G is considered accurate. So if I write a little sentence here to communicate that, 1.6% accuracy is less than the 10.6% uncertainty. Therefore, the student's value of G can be considered accurate. There we go. I'll have to check myself against the mark scheme, but it looks as if this question was worth 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's another 12 out of 17 we've achieved, or we calculated that last time. I think that ended up being 17%, so there's another 17% achieved.